So here we have taken one of the statements, position equals to initial plus rate in multiplied with 60, and here it is being assumed that position, initial and rate are of floating point, or we can say real type, because this statement which is being presented as in Pascal language. So it is in Pascal, the fractional values are being considered as real, or in C it is being considered as a floating point. So let us assume that these are floating points and 60 is an integer constant, right? Now, if you see the objective of the lexical analyzer is to generate the tokens. So how many tokens are available if we consider this is in C language, and this is an equals to how many tokens can be generated here along with this process. So here we'll talk about position is one of the tokens, because token is nothing but the specific sequence of characters generating a word. This could be another token. This initial could be another token. Plus is a token. Rate is a token. Star is a token. 60 is a token. Now, the moment you're talking about these elements, now please tell me, out of all these elements which I have highlighted here, which are known to the compiler predefined and which are not predefined.
60 asterisk and plus.
No, 60 is also not being predefined. The predefined elements, which we call it as an operators, keywords, right? All those things are predefined. So star plus equals to are predefined. So we cannot make any changes to the names, right? The names will be represented as it is. But the moment we talk about all these elements, position, initial, rate, and 60. So these are identifiers, and this is a constant. And to prepare, and I hope all of you remember that while you are representing an identifier or we are representing a constant, we follow a certain rules, right? Now that rule may lead to different types of identifiers. So for that particular purpose, if you can just check the output of the lexical analyzer or the scanner, we have represented position 1 as an ID1 equals to remain as it is. Initial is being considered as an ID2, plus remains the same. Rate is being considered as an ID3. Star is mentioned as a star itself, and 60. I have kept it 60 because there is only one constant in the string. But if it is multiple constants, then I could have made it constant 1, constant 2, and so on. Right now, the question is, the moment I'm formatting or generating all these tokens, now the position is no more being identified as a position, it will be identified as an ID1. Now, how exactly I know that ID1 is representing a position, or ID2 is representing the initial, or ID3 is representing the rate, likewise. So for that particular purpose, yes.
Sir, it can be set from the symbol table.
Right. So for that, we create a symbol table which keep track of these identifiers, constants, or in general, we call it as a token, which are not known to the compiler previously, right? So the tokens which are going to be generated based on the current program. So this symbol table is going to be maintained for each and every program. The moment you start executing a program, the symbol table will be created for that particular program, and post execution, the symbol table will be destroyed, right? And the symbol table will only contain the information which are additional to the compiler, for the information of the compiler, right? Now, what kind of additional information? So this symbol table will contain similar, the first element is position and its alias names like ID1, ID2, ID3 will be represented like here, ID1, ID2, ID3, and so on, right? So the number of identifiers or the number of constants, whatever is being identified, can be listed out, and the alias names will be represented. Now, why exactly it is necessary? Now, for the rest of the phases are going to take or are going to access these alias names. They are no more going to consider as a position or initial or rate. So that's why, if you remembered, I have told symbol table, the symbol table is connected to all the phases. Bidirectional, all the phases And if it is necessary, all the phases is capable of updating the symbol table if it is necessary, depending on the requirements. Right? This is the first part of the task of the symbol table, what exactly we have generated, ID1, ID2, ID3, and all. Okay. Now, a set of tokens now is being
Sir,
thrown. Yes.
sir, symbol table generates ID1, ID2, or it stores that ID1 equals to position, ID2 equals to initial.
The symbol table will be generated by the lexical analyzer. Okay. So the lexical analyzer will create this symbol table, right? And it keep track of the tokens. The symbol table will keep track of the tokens which are not defined or predefined by the compiler. Why? What is not predefined by the compiler? For example, variables or the constants, right? Why exactly so? Because every programmer doesn't have got the same mindset to create a variable. So for an integer declaration, you may utilize a b c d. Somebody else may utilize int I comma j comma k. So I, j, k, a, b, c, d, everything is considered as an integer, but for different programs there are different names. So to represent those names in a sequential and in a proper manner, so if it is a b c d for one program, then I'll say is an ID1, ID2, ID3, ID4, and so on. So for the other program, it might be IJKL, so it might be again considered as an ID1, ID2, ID3, ID4. That's why this symbol table will be created by the lexical analyzer, and the extra information which is not part of the predefined constraint of the compiler will be defined here, right? The predefined
Yes, sir.
okay.
Yes,
Now
sir.
once the tokens has been identified, all the tokens will be thrown or as given as an input to the syntax analyzer to generate a parse tree. Now the purpose of the parse tree, what is the purpose of the parse tree? Is to go on and find out a proper way of evaluation. Simple. It's a kind of an proper way of evaluation, how exactly an evaluation can happen. Okay. Or not exactly the evaluation, how exactly the syntax could be presented. Okay. Now what is syntax? Syntax is the form of writing a program, right? Syntax is a form of writing a program. Now this parse tree is going to help us out to identify the proper form of writing a statement. Now, right now, this, what kind of statement this one is all about? It is an assignment statement. In the assignment statement, it is a composition. In the right hand side, it is an arithmetic expression, and the left hand side, it is a variable. So first of all, the arithmetic expression has to be evaluated and need to be assigned to the left hand side. Okay, that is the basic objective. So for that particular purpose, first of all, we have to check the syntax of this arithmetic expression, and then we will be checking the syntax of the assignment statement. So the syntax can be verified by the parse tree the way we are expecting the syntax to be. Okay. Now let me write one wrong statement here, saying that PW equals to A plus B. Now what exactly you consider? There is a space here. In a C language, I have represented this statement. What exactly this means? Is it an assignment statement? Then I'm a class, Raj. Good morning, class.
Sir, there is an error.
There is an error. So who decides that error? Now, then just tell me how many tokens are there? Can you identify the tokens?
6.
1, 2, 3, 4, 5, 6, 7.
Okay, sir. Yes, sir. 7.
7 tokens. Now, if I'll throw the 7 tokens to the symbol syntax analyzer, this should generate me a parse tree. But in this case, the parse tree will not be generated because the tokens here will not be able to identify their right positions, where exactly they are supposed to be present. Now, there would be any relationship between these tokens. There is no relationship between these two tokens, by which you are saying that there is an error, or the compiler will say that there is an error. That is a task of the syntax analyzer, right? I hope you have understood what exactly I meant to say on that. Now we will see how exactly that is going to happen later, whenever we will discuss about the syntax more on that. But ideally, it is simply checking the syntax, whether you have given a semicolon, whether you have given the say for example, you might have missed out some time in a C programming, you might have represented like this. In initial days, right? And this must have shown you an error. Yes or no?
Yes.
Yes, sir.
What is the error?
Condition.
So there is a
Condition,
yes
sir.
in if condition.
As it is a if statement, there is a syntax error here. So this is a syntax error. The right use of the operator. So every statement has got their own rules and regulations, right? So if we follow the rules and regulations, then we should able to generate a correct parse tree, right? A correct parse tree. Now, what is this rules and regulations? Just now I have shown an example. In an if statement, this should be a conditional statement, right? So if it is a conditional statement, there are how many type of conditional statements are there? Yes. Majorly, conditional statements is of kind of a binary expression, because all the operators greater than, less than, greater than equals to, less than equals to, double equals to, or not equals to contains two elements or two operands, both the sides. Now, if both the operands are available, within that the operators are fixed. Out of this set of operators, I'm going to utilize this. So this is the rule for a conditional expression. Now, if the operator is not matching, definitely this is not going to give you one correct parse tree, right? This will generate you and throw you an error. This will not match with the rules. Okay. Now the parse tree is generated. Now what next to the parse tree? The next to the parse tree is to decide the behavior. Okay. Now what is this behavior is all about? Now let's say you are computing something like a equals to 2 plus 3 multiplied with 5.1. What is the result? What is the value of A?
17.3.
17.3.
So typecasting.
Okay. Now, how exactly you have evaluated this? I'm talking about you, not by the compiler. Now, the moment you multiply this one, this is
Got a decimal value. Yes.
this is an element, integer element without a decimal. This is an element with a decimal, right? The moment you operate on this, the result is going to be on a decimal, right? Now, the compiler does what? It makes it into 3.0 into 5.1, right? Now executes it. Whatever result 15.3 is going to be added with 2.0, and the result is going to be 17.3, which is being assigned as an A. Now let's say, for example, we have declared a int A. Now what will happen?
17.
17.
17. In the recent compilers, in the online compilers, it is by default, it is converting into 17, but in original, it should show you an error. Now, if you compile this expression in a Turbo C compiler, the oldest one, it will show you an error. Now, what is the error? There
The
is,
decimal to integer.
yes,
Type
there is
mismatch.
series of 2 bytes, and the floating point value here is 4 bytes. Now, 4-byte value cannot be assigned to a 2-byte location. Okay, that's how it is. So that's the that kind of error normally will be generated if we are going to use an old compiler. But the online compilers does what? They are just trying to reconvert it to the integer to show you the result. But in original, it is not exactly the same. So, but I have not told you when I am going to compile, execute this part of the code. This is not going to show you an error because 3 is being automatically converted to 3.0 or 2 is being automatically converted to 2.0 because this is implicit type conversion, and the other one which I've talked about, integer a assigning a floating point, this is
Explicit.
explicit type conversion. Now this kind of elements are being taken care by the semantics, the behavior, it corrects the behavior, how exactly it should behave while you execute it. If the behavior is not being identified by the properly, then probably you are going to generate a wrong result at the end. Okay, now post that, this is the analysis is being completed, everything is correct. Now what exactly correct? All the words or the tokens has been identified as correctly, then the syntax of the statements are identified correctly, and the semantics has been identified correctly. So my analysis is complete. So if once the analysis is complete, then I can jump into the synthesis, where we will be looking into this intermediate code optimizer, code generator. Right now, this analysis is very much important to work on this. Okay, majorly, the moment analysis is done, we have generated with this kind of a tree, parse tree or syntax tree or abstract syntax tree. We'll talk about more on that, but this is more or less will decide how exactly your outcome or the machine code is going to behave. So this element here presented as called as an syntax tree, abstract syntax tree, or an attributes, representing attributes and all, because it is representing the behavior, will decide upon how exactly your code is going to be generated phase wise. Because you cannot, as I said, you cannot execute the complex instruction at one instant or one stretch, right? So to execute the complex instructions, what exactly we need to do is we have to subdivide the expressions into smaller ones. The way I have done it here, you can check every step within the parse tree represents one expression, one sub expression in fact. So every intermediate node, if you can observe every intermediate node, and the moment we are considering intermediate node, all the intermediate node in the execution process need to be considered from the bottom to the top, right? Need to be considered from the bottom to the top. So for that, first element is into real 60, that is the intermediate element, right? How many operands? Only one operand. So this is an unary operator, one operand. Where exactly the result will be stored? The result will be stored in some temporary location assigned by the compiler. You need not record to assign that. It has to be assigned by the compiler. Your intermediate code generator program has to do that. Post that, again, it is a star. Now what is star? Star represents two operands, one here and another one is the result of I into real. So result of into real is present in temp1, will be multiplied with id3. So id3 is going to be multiplied with temp1, and again there is no exact location to be stored, so it is being assigned to temp. So here the result is being assigned with temp2. Now this temp2 is going to be added with id2. So the next step is something like that. id2 plus temp2 is stored in temp3. So my result now here it is in temp3. Now then it is an assignment operator, right? In the assignment operator, id1 will be allocated with temp3. So each and every step or each and every intermediate node is being represented as one sub expressions in the code generator, right? In the code generator, this is called as an intermediate code generator, not exactly the code generator, intermediate code generator, ICG. In short, we call it as an ICG, right? So in that, hope it is clear now.
Yes.
Yes, sir, it's clear.
Now, next objective is code optimizer. As I said, this is an optional phase. If optimization is possible with this set of codes or lines of codes, then we will go through this. If optimization is not possible, then we can skip that. Okay. So code optimizer will do what? It tries to minimize or maximize the lines of code. It tries to minimize or maximize the lines of code to reduce the time of execution, right? To reduce the time of execution. Now, how exactly it can do that? So this can be done in various ways. For example, say if you can say certain values are constant across the whole program, need not be required to be calculated whether during the runtime. So the compiler is capable of calculating the value and output the result at every place wherever it is being utilized, right? Some redundant expressions can also be removed. Okay, some common expressions can be removed whose values doesn't change throughout the program. We'll talk about that more, but in this particular example, if you can see, int to real 60, that means the integer value of 60 to be converted to a floating point value, and the floating point value is always going to be 60.0. It cannot be 60.1 or 60.2 or 60.3. So the compiler identifies that, saying that it is into real 60 means it is always going to be 60.0. So instead of calculating during the execution time or the run time, it calculates during the compile time. And using 60.0, okay, and is being multiplied with ID3 and stored in a temporary variable. Okay, now next, in these two expressions, what exactly it is done? Where if also see, ideally it is being represented as ID1 equals to temp 3 is equals to ID2 plus temp2. Now what exactly this does? A redundant assignment. This kind of expression is called as a redundant assignments. First, I'll be computing this, then I'll be assigning to temp3, then temp3 will be assigned to ID1. Instead of that, what exactly we can do is, or the compiler is going to do is, directly it is going to assign it through ID1, right? By which we can reduce one more step. We can say that redundant assignments can be removed. So for that, we talked about ID1 is equals to ID2 added with temp1. Now the 4 instruction set and now is getting reduced into 2 instruction set, and definitely it is an increase, and definitely it will give you a better performance in the execution time. Okay, now post that, the code generator will generate a set of assembly level language code depending on the type of expressions available. Okay, now this in the code generator, this code generator must have got the information of how many registers, right? And that how many temporary variables it can utilize. All those things must be available, because you have to play, or this code generator has to generate the final assembly level language code based on the available registers. Now, say for example, in the current processor, the number of registers is 16, then it has to deal along with those 16 registers and best utilize the best efficiently the use of these registers, best efficient use of these registers. Okay, so that's how the code is all about. Now here, if I'll just explain this part of the code into a code generator. Now it says move ID3 to register 2. Now ID3 contains a value. Now it has to move to the register for some kind of operation. Okay, unless until the value is moving from the original memory location to the register, the compiler or the it cannot be executed, right? So move the value of ID3 into register 2. Then it says multiply 60.0 as it is a numeric value, direct value, it's directly giving 60.0 along with the register content of R2. So R2 contains the register, the ID3. Then again post, we have completed all this computation. Now you can observe we have completed the multiplication 60.0 into R2 and the result is being present in R2. This temp 1 result is being present in R2. Now again we are talking about move ID2. So the next operation is ID2 to R1. So register R1, it is the value of ID2 is being moved to register R1. Then add R2 along with R1. So the temp 1 result is being there in R2 and ID2 is in R1. So the both are being added and the result is being there in R1 register. And then we are moving R1 into ID1. So it is a sequence of machine instructions in the assembly level language code which generates you the or which helps you to identify. So the basic target objective of the code generator is to best utilize the registers and the other resources to generate an assembly level language code. Any doubts here?
Okay.
Perfect. So this is an overall view of the compiler, how exactly a compiler compiles a particular program in 6 different steps along with the help of a symbol table. And I have not shown you the other part is the error handler. I will show the error handler in a while's time or might be in the subsequent discussions whenever we are going to have an kind of an error, right? I'll show that in that particular section. So now post this, what exactly we will do is we will be moving on to the what exactly you can say is all about the individual phases, how lexical analyzer works, how syntax works, and how semantic works. We are going to spend maximum of the time on the analysis. Post that, we will assign or we will discuss about the synthesis, which is called as an intermediate code generator and your code optimizer and your code generator. We'll spend, in fact, we can say that it is in 75% and 25% of the content what exactly we are going to share. In the analysis, it is 75% and in the synthesis, it is all about 25%. Right? So let's move ahead on to the next topic. That is your individual phase, that is lexical analyzing. I hope all of you have written down the lexical and role of lexical analyzer previously.
Yes, sir.
Yes, sir.
There are 4 things which I have mentioned. One is your tokens, identification of the tokens, removal of blank spaces, and what else? It has to read the source program, right? So the first rule is to read the source program.
Error handler.
Yeah, read the source program. The last task is to collate along or work along with the error handler to display the errors to the users. Okay. So once the source program is being given to the lexical analyzer, we have seen in the previous discussion that lexical analyzer throws a set of tokens, identifies the set of tokens and throws it to the parser for sequencing or finding the parse tree. Now, let me give you one case. I have given you something like a set of tokens, ID1, ID2, ID3 equals to plus minus. This set of tokens I have provided to you along with semicolon. Now give me a statement in the syntax, how the syntax is going to behave along with these tokens. Now these tokens are being given to the syntax. Can the syntax analyzer check the syntax?
No, sir. So they are randomly ordered.
Yeah, they are randomly ordered, right? Now, what could have been the best case for the syntax analyzer? In what order, if the syntax analyzer will say, identify the tokens, then the syntax and it is easier for the syntax analyzer to work along with this.
If there could have been a proper equation or anything expression.
Okay. No, not exactly.
Like
Expression is-
ID1 equals to ID2 plus ID3. Something like this.
No, not exactly. We are very close to that, but not exactly the same.
So if they were ordered in the way they were read,
Who will give you the ordered element? Lexical analyzer will give them ordered?
Yeah.
No, not exactly on the same. Though it is going to work in that particular order which you are talking about. It must be supplied. The tokens must be supplied to the syntax analyzer in a particular order. As you said, it is correct, in a particular order to check the syntax. Now I cannot assign, I cannot throw another, let's say int, float, and 3 identifiers or 3 tokens, ID1, ID2, ID3. There is no order in that. Int will be assigned with ID1 or ID2, or float will be assigned with ID3, something like that. There is nothing mentioned in that perspective, right? So for that particular purpose, the lexical analyzer and the syntax analyzer has to work in a sync. It cannot be independent phases. I have shown in the previous slide, while I have talked about example, and I have shown lexical analyzer is an independent phase, and syntax analyzer is also an independent phase. But actually, they are not independent; they are dependent on each other, as shown here. Right? If the lexical, as I've shown you, lexical analyzer throws all the tokens at one instant to the parser will be helpless, and the parser cannot check the syntax. So once the lexical analyzer starts reading the source program, the first token will be identified and will be thrown to the parser, right? Depending on the rules and regulations the parser is going to follow based on the first token, the parser will request for the subsequent tokens. The parser will request for the subsequent tokens. Until unless the parser requests for the subsequent tokens, your lexical analyzer is not going to generate a token for the parser. Are you getting it? What exactly I'm talking about? So for example, I have represented something like A is equal to B plus C. Now the first token, this is the source program. I have given as an input to the lexical analyzer. The lexical analyzer will do what? It will first read this and pass it as a token to the parser. Then the parser will generate or request for the next token. Until unless the request is generated, the next token will not be identified. So based on each request, the token will be generated and will be passed on to the parser. And the way the tokens will be, now in that case, the tokens will be in a sequence, as we are talking about, in an order. The moment the parser will identify that a one statement is completed, it will generate the parse tree and proceed further. Okay, are you getting it? And in the subsequently, the moment tokens are generated, if it is necessary, the symbol tables are going to be updated.
Sir.
Yes.
Sir, but like you mentioned earlier that there was a question ID1, ID2, ID3, and then plus minus equals to etc. So in that case, how it will work?
Which case? I'm not getting it.
So previously you made a block, right, in which you wrote ID1, ID2, ID3, and then plus minus equals to semicolon.
That case will never appear. But exactly I meant to say that if I will consider this as an independent page. We'll read the source program and will throw all the tokens at one instant of time to the parser. Right? You're talking about this one, no? ID1, ID2, ID3, sorry. ID1, ID2, ID3 plus minus. So you're talking about this one, right?
Yes, sir.
Okay. Now let me give a statement. A equals to B plus C multiplied with 60. This is a previous same statement. Now this is being given to the lexical analyzer. The lexical analyzer will generate ID1, ID1 equals to, next is ID2, next is plus, next is ID3, next is star, next is 60. Now tell me, now if I'll give this input to the syntax analyzer, what the syntax analyzer will do? How exactly it will identify the relationship between each token?
We have to give that one by one.
Yes. So we have to give, the moment I'll give the first one to the syntax analyzer, then the syntax analyzer will demand for the second one until the syntax is not complete. Until the syntax is not complete, it will demand for the second one. It will demand for the third one. Then it will demand for the fourth one, and so on. Right?
Sir,
That's how.
sir,
Yes.
like we sent ID1 to the syntax analyzer, then
Mhm.
syntax analyzer demanded for the another one. Then we sent ID2. Since those two can't be together, then it will give an error.
Yes. If it is sent an ID2, then it will give an error. Right.
Okay, sir. Got it.
So the lexical analyzer, the moment it is a source program, it cannot read arbitrarily. No, it has to read in a sequence. Right? All the characters are read in a sequence.
Yes, sir.
The moment it is read in a sequence, the first token is being read in a sequence identified when the read pointer is present over here. Now, the moment parser generates the next token to be read, then the read pointer again starts reading towards the next. I'll talk about more on that, how exactly the tokens are getting identified and passed on onto the parser, and how exactly the source program is being read and the tokens are identified. That's also very important. Reading of the source program and identification of the tokens. So why exactly I'm showing this is, though in the previous case I have shown lexical analyzer and syntax analyzer as two independent pages, but in actual they work in coordination. Now why exactly they are made independent? Because of the simplification or simpler design of the compiler. Now if we'll combine them together as one page, which is ideally to be, it creates lots of complexities while developing both the phases as a single phase. So for that, it is being made as two different phases having two different tasks. This will generate the token, this will generate the syntax or check the syntax, but they work as a single unit. Okay, that is the basic objective. Why exactly the dependencies are being available at this particular point. So that's what is being presented here. Why then I might ask that why exactly they are considered as a separate as they are working in coordinated way, because of the simplification of the design process, efficiency and portability issues are also being there. So it resolves many of these issues while separating all those elements as separate phases. Now, in the lexical analyzer, these are three terms: tokens, patterns, and lexemes, which are going to be utilized a lot of time. Maybe literally, if you think all the meanings of these three words, tokens, patterns, and lexemes are same, but having different representations or different objectives. So to start with a token, what is a token? I hope all of you don't read this. I hope all of you have gone through tokens many a times in the programming languages. Yes. No idea.
So smallest individual element in a program.
Smallest individual element in a program, right? So what exactly we can talk about in tokens is, if you can give some examples, like identifier is a token, and then your operators are tokens, special characters are tokens, then your literals, many tokens are available. Okay. Now our objective is, that is the output of the lexical analyzer. Now, how exactly the tokens are being identified into their categories? Like we color as in categories like identifiers. Another category is keywords. One more category is operators. In the operators, we have got many categories like arithmetic operator, logical operator, relational operators, bitwise operators. We have got many categories of tokens in that. Then we have got constants, integer constants, floating point constants, numeric constants, or you can say alphanumeric constants, character constants, string constants. All right. Then we have got your special characters like semicolons, comma, dot. Many things are available. So how do we categorize them? Yes. How do you categorize that a set of words or a particular word is in the category of identifier, or the
By
category
following a pattern,
following?
like these two things are doing similar kind of work.
These two things are similar kind of elements, right? So I hope now you have heard about, now you have talked about pattern. Okay. Now the second
Yes, sir.
component which I'm talking about is a pattern. Right? It's a rule describing or for a particular type of token. It's a rule for defining a type of token. For example, identifier. In C language, identifier says it starts with a character and underscore following with letters or digits. Okay. In operators, we have got arithmetic operators type star, plus, minus, percentile, division, and all those things. Similarly, I've got relational operators. If we talk about keywords, every keyword has got their own specific pattern. Like int is a keyword, so it is a pattern. Float is a keyword, it is a pattern. Likewise. Now, what is a lexeme? Token is the output, right? Pattern is a rule. Now, the lexeme is the sequence of characters which is being matched along with the pattern to identify the token. So the moment I start reading the source program from the left towards the right, we are going to expect it that identify a set of characters. A set of characters, right? This set of characters will be considered as lexeme. This set of characters are going to be considered as lexeme, and this lexeme is going to be compared or matched along with the pattern to identify what kind of token we have found. Whether we have found an identifier, or we have found a keyword, or we have found an operator, and so on. Right? I hope now you have all understood what is the purpose of these three words. Lexeme is a blind set of any set of sequence of characters from the source program, and this lexeme is going to be matched along with the pattern or the rules, And if the pattern matches, then we identified the token. Simple. Then we have identified the token. So we'll stop here. Proceeding further, we'll have some examples on these 3 words and how exactly this is going to help us out in specifying or identifying the elements. Okay, thank you very much.
Sir, please send the
Excuse me,
recording.
sir.
Yeah, I'll update the recording in the classroom group. Okay.
Okay, sir. Okay.
Excuse me, sir. Roll number 10, actually, when I joined, the attendance was over, so I thought that after the class I would have tell you.
Okay.
Roll number 10.
Okay, I'll update that.
Thank you, sir.